So, welcome student to the next class of Introduction to Nonlinear Optics and its Application course. This is now lecture number 22. So, today we in this lecture we have the topic type of type 2 kind of phase matching and then symmetry in the nonlinear susceptibility. So, two very important topic. So, in the previous class what we have done is in type 1 phase matching. So, let me again remind. So, type 1 phase matching can have two kind of system. So, in type 1 phase matching, two ordinary wave can merge and generate an extraordinary wave, or two extraordinary wave can merge and generate an ordinary wave. So, two ordinary wave of frequency omega can create an extraordinary wave, or two extraordinary wave of frequency omega can generate a ordinary wave of frequency 2 omega. The index structure for two cases are distinct. If I now see here, then in first case the condition has to be n of ordinary wave at particular frequency is greater than n of extraordinary wave at that particular frequency. So, this kind of crystal is called the negative crystal because NO is greater than NE. On the other hand, for other scheme, that is EE is equal to O, this system, that means two extraordinary wave when generate one ordinary wave. For this system, the refractive index of extraordinary wave at particular frequency is greater than the refractive index of the frequency omega. So, when these two conditions are there, we have two different kind of system, but both the cases we generate the second harmonic waves and able to generate also the angle at which these things can be possible, and it is fall under type 1 phase matching. So, in type 1 phase matching we are using either negative crystal or positive crystal, and the system is where we have two ordinary wave to generate one extraordinary wave or two extraordinary wave to generate one ordinary wave. Apart from that, there is a possibility that we can combine these things. That means two, instead of two ordinary wave, if you see carefully here, we have one extraordinary wave and one ordinary wave that can generate one extraordinary wave, and one extraordinary wave and one ordinary wave can generate an extraordinary wave. So, here somehow it is become theta. So, it should be E. So, let me write E plus O can generate E. This is one system under type 2 phase matching. E plus O can also generate an ordinary wave. This is a mixture of these things. So, this is called type 2 phase matching. So, let us understand what is going on. So, one ordinary wave, in this case one ordinary wave, one extraordinary wave is creating one extraordinary wave. This is one system. One extraordinary wave, one ordinary wave is creating one ordinary wave. Both the cases, this is omega frequency, this is at omega frequency, this is at 2 omega frequency, this is at omega frequency, this is at omega frequency, and this is also has 2 omega frequency. So, these two conditions are there. So, now after having the knowledge of this type 2 kind of phase matching, we can need to find out what is the refractive index representation for this type 2 and this type 2 phase matching with this system. So, one ordinary and one extraordinary leads to one extraordinary. In this system, if I write in terms of k, so k 1 is a frequency, k 1 is a propagation constant at frequency omega 1 or omega. So, k 1 and ordinary, k 1 and extraordinary is generating k 2 at extraordinary. So, this is the scheme of ordinary plus extraordinary is equal to extraordinary. So, now k 1 can be represented at frequency. So, we know that k several times we are using omega by c and n. So, k 1 means frequency omega. So, omega divided by c and n I need to write this is ordinary. So, ordinary omega. K 1 at extraordinary omega by c n e omega. K 2 is what? K 2 is the frequency of at omega 2 omega. So, K 2 is a frequency at 2 omega. So, I write 2 omega divided by c n of e because of e and 2 omega. So, after having all this information, so in the next step what we will do, I just cut this omega divided by c term altogether. If I cut, then we have a new kind of expression which is n of omega n e of omega is equal to 2 of n e of 2 omega. This is the type 2 phase matching condition, but this condition is for E plus O plus E tends to E system. In the similar way, if you do O plus E tends to E system, that means one ordinary wave, one extraordinary wave is leads to one, sorry, this is O because already we have done these things. So, let me write once again very clearly, ordinary wave, one extraordinary wave leads to one ordinary wave. So, what should be the expression? The left hand side will remain same, but in right hand side we have different because this is the ordinary wave of 2 omega. So, I will have 2 of ordinary wave of 2 omega. Exactly the same calculation we have done in the next system. Yeah, this is the system where we have one ordinary wave and one extraordinary wave that leads to one ordinary wave. So, again in terms of k we have the similar thing, only thing that is changing here is O. So, at the end of the day we are generating the ordinary wave having 2 omega frequency. So, we have omega c, 2 omega c n of 2 omega, and in all the cases if I now cut omega by c, then we will have n of omega, n e of 2 omega is equal to 2 of n o of 2 omega. So, these two are type 2 kind of phase matching, but this type 2 kind of phase matching in order to achieve it is not easy. We need to maintain many things, that many conditions are there for which we can have these things, but we can always generate the angle theta for which this can be possible. So, let us check what we have in the next slide. So, next thing we will going to learn is symmetry in nonlinear susceptibility. So, here let me go back to this type 2 phase matching. In type 2 phase matching we have two different condition, this and this, but this for these two different condition again it is possible to find out the direction, but it is a complicated one, but one can find out the angle theta by using this expression. It will be a complicated kind of expression, but it is possible to find out some angle at which these things are valid. Okay. So, next, symmetry in nonlinear susceptibility. This is a very important thing that we are going to study or in this particular course, that this symmetry and all this. So, let us go back to our original equation related to nonlinear polarization and electric field. Well, this is the component form of nonlinear polarization and electric field. So, ith component of nonlinear polarization can be written in terms of j and k, and this is the susceptibility components, the tensor components of the susceptibility I j k. So, now j k is the indices which is repetitive here. So, we know that when these indices are repetitive, eventually we have a summation sign here. where I j k is something. In this case not I j, it should be j k. Okay. So, it is something like one summation sign is here and this sum is over j and k. But we never use this summation sign because of this Einstein notation. We just remove that. It basically reduces lot of energy, and this combustion equation become more compact. Now, the question is, if we have I j k here in terms of D matrix, this is 2 of epsilon 0 d I j k. So, how many D components are there? Now, if I calculate I j k, there are 3 components. For each one component, say I and j fixed, if I and j fixed, then k component can vary 1 to 3. So, I have 3 components. For each 3 components, I will have another 3 components for j, and for each j components I will have another 3 component of I. So, we will eventually have 27 different component of this D when D I j k all are vary from 1 to 3. In this matrix form, I try to write all these 27 elements, and if you see what is my first term 1 1 1, then 1 1 2, that means I am not changing I and j remains same, I am just changing k value. So, this is 1 1 3. Then for D I have 1 2 1, 1 2 2, that means this is for this case I am just fixing I and j at 1 and 2, and then changing the last one 1 2 3, then I 3 1 3 1 3 and then 2. I am not changing 1 and 3 1 and 3 and 3. In the similar way, now I am changing the I value 2 1 2 1 2 1 1 2 3 2 2 2 2 1 2 3 and so on. So, if you write all these things in some sort of matrix form, you will find that there should be 27 elements. These 27 distinct elements one can have once we have the entire picture. So, that means for ith term, only for ith term, if I is fixed, we should have that much of element. How many elements are there here? 1 2 3 4 5 6 7 8 9. So, only for ith element in the right hand side I have 9 different elements in my hand. So, that is a very cumbersome thing, that in order to have one polarization component in the right hand side, I have 9 different D elements or D matrix. Okay. So, next let us see what we have. So, now fortunately we have some kind of permutation symmetry in this particular system. What is the permutation symmetry? So, let us write here. So, permutation symmetry suggests that if I want to find out a polarization at particular frequency, say omega 3, this omega 3 is generated due to 2 waves of omega 1 and omega 2, then I can have the susceptibility with the frequency omega 3, it is generated omega and omega 2, and epsilon this electric field of jth component and electric field of k component have this frequency omega 1 and omega 2. Now, if I interchange the I and j component, then we will have a similar expression. So, here what we are doing, we are changing the ith and jth component. So, if I change the ith and jth component, then this term here and this term here and this I j will also shift their location, but in the left hand side we have the same quantity again. So, that means if I try to understand, that means susceptibility I j k and susceptibility j k I k j, both the cases I will have the same. So, if this is equal to this, then we can readily say that susceptibility at I j k, susceptibility of ikj are same. So, that means I can interchange these two things. So, these two things are same. So, now if ijk and ikj they are same due to this intrinsic permutation symmetry, then the D matrix significantly, there are 27 elements. So, these 27 elements can significantly reduces to 18 elements. So, how these elements reductions are possible, let us see. Well, here we can see the D matrix has 27 different elements, is the first one, but we have this condition in our hand. So, this is the condition due to the permutation symmetry. I have this in my hand, that Dijk is Dikj. Once we have Dijk is Dkj, then if I look very carefully, then here in this from here to here, we find that this components and these components are same. All the components which are marked with different colors are same. If you find these pairs are same value. So, D12 and D21, these are the same, because if I interchange 2 to 1, 1 to 2, this will be the same quantity. Again, here we have 1 3. So, somewhere I should have 3 1 and 3 1 is sitting here. So, these are the same colors. So, these two things are same. So, these same, these two things are same. Here in the first row also D12 and D32, D123 and D132, again these two things are same. We have another components also D212 and D221, again these two components will have the same value. These two things will have the same value. But if you note that these components 1 1 1 1 1 1, it will not going to change, because even if you change it, it will remain the same quantity. Here also 3 3 3 3 3 3 will not going to change, 2 2 2 2 2 2 not going to change. So, how many independent components now we have after this permutation using this permutation symmetry? The answer is 18. So, these two pairs, so how many components are 9 here and 9 here. So, all these 9 components are same, these 9 components and the 9 components are same. So, now that means we can reduce these 18 components to 9 components, and the 9 components are already there. So, 9 plus 9, so we will have 18 components. So, we will reduce from 27 to 18, we reduce 9 components because of using of this permutation symmetry. Once we reduce this permutation symmetry, the next thing is to rewrite the D matrix in a more compact way. So, before going to write this D matrix in a more compact way, we need to find out what should be the value of P x. So, this is the same thing we are writing. So, P x is epsilon 0 I j k, and now if I want to find out the xth component, I should write d x x, d x y, d x z, also d x y x, d y y, then d x is same for all the cases. So, just I am changing the next two indices and this. So, there should be 9, there should be 9 components, 1, 2, 3, 4, 5, 6, 7, 8, 9 components. But again I am using this permutation symmetry, and once I use this permutation symmetry, I will reduce this to 6 components. So, for one P x initially it was 9, similarly for P y we have 9 components, for P z we had 9 components. So, total 27 components, all these 27 components are different D, but for this permutation symmetry we can reduce this to 9 components. So, this is one component x s, this is y one component, this 9 independent components are now reduces to 6 independent components with this permutation symmetry. So, once we have these things, you will find that d of x y is equal to d of x of y x. These terms are here, both the cases, because in both the cases this multiplication term E x E y is same. Here also the multiplication term will be E y E x. So, we will have a 2 term common here. So, we have 2 here, 2 here, 2 here for all these cost term. X x, y y, z z should have independent, and we have the square term here. So, this is the way to write P in terms of E with D matrices. So, if I now write these things in contracted form, then we have something different. So, after having the knowledge that for this permutation symmetry, this D matrix now reduces to from 27 to 9, 27 to 18, and then for each we will have 6 component, one for one px we have 6 components. So, let us go back to this D matrix once again. For this D matrix, these terms are similar terms, all the terms having the same color on the similar terms. So, once we have these similar terms, then we will not going to write all these things once again, because this is called the contraction of indices. Because if 2 3 is equal to 3 2, so we will not going to write every time these 2. Instead of this, we will write some different, and here this different thing is 4. So, 1 1, so 1 1 these components I write at 1, 1 2 2, that means this one I write 2, 3 3 I write 3, 2 3 and 3 2, which are eventually same thing as I mentioned here, I write 4, 3 1 1 3, which are eventually same, I write 5 and 6. Since there are 6 independent components, I write these 6 independent components in more shorter notation, or I shrink the indices. So, D 1 1 I write D 1 1, D 1 2 2 I write D 1 2, D 1 3 3 I write D 1 3, D 1 2 3 I write D 1 4, D 1 2 3 and D 3 2 1 is same. Similarly, D 1 3, D 1 1 3 is same, D 1 1 2, D 2 1 is same, and I write this as 1 6. So, once we have this contraction, so the D matrix become more compact, and this is the final compact form of D matrix. Initially, we have 27 components, and now we have 18 different components. So, here we have this, for this we have these things 1 2 1 3 1 4. So, 2 1 2 2 2 3 2 4. So, now interesting thing is that previously we have 27 components. Now, after using this permutation symmetry and then contracting the coefficients or the indices, I now reduces to 18 different components. So, this is the form, the compact form of D matrix. So, in the next lecture we will find that again we can use some other symmetries, so that I can reduce the elements of the D matrix further, and then by using some kind of symmetry operation we can also reduce the the elements. Some of the elements will be same, some of the elements will be 0. So, initially even if we can see that there are 18 different elements can be possible to D matrix, but later we will going to find that most of these coefficients are going to vanish, and we will deal with only few elements of the D matrix, and in all the cases we use some kind of symmetry operation. So, with this note, let me conclude this class. So, in the next class we will start from this D matrix and contraction of element etc., and try to find out what the symmetry operation is, and by applying the symmetric operation how do I find the exact value of these elements. So, thank you for your attention. See you in the next class.